So here we'll talk about the photoelectric effect and a little bit about how it came about. It was kind of a happy accident. It was first observed by Hertz when sparks flew from a negatively charged electroscope when exposed to light. And this was the first observation, and his assistant later ran some tests and experiments with this idea, and it wasn't until about 20 years later that it was explained by Einstein. So what is the photoelectric effect? Basically what it says is that the energy of a light wave is bundled into small discrete packages. This is what we call light quantum or photon. So when this light is shown on a metal surface, the electrons have enough energy to escape from that surface. So about the effect, what should we expect? In classical physics, it'll tell us that an increase of intensity means that there's going to be a higher number of electrons released. And an increase in time will get greater energy. Light is a wave, and so the metal is going to be absorbing that energy from the wave. So the more time it's exposed, the more energy it'll get. Now the observations or through experiment, that's not quite what we see. We only see that at certain frequencies. So if the frequency of light is below a certain value, there's no electrons released. It's kind of a sharp cutoff, an all or nothing type of thing. So the difference between what we expect and what we see is different. So that's kind of another twist in the physics world. So an experiment was set up, and what happens here is you have a vacuum chamber. So that means nothing can really get across unless you really want to. It's a circuit with a vacuum chamber and a battery. Now, in this experiment here, the electrons here are desperately trying to get over here towards the positive end of the circuit. So when you shine light on it, they can be released and whatnot. So but they can't jump across unless they're liberated first. So the experiment, what happened was they reversed the batteries, so that means the electrons can't make that jump unless the energy is higher than what's required to jump. So what happens is, you shine the light, you turn up the voltage, and then until there is no more current. At that point, that's what we call the stopping potential. And this stopping potential depends only on the frequency and not the intensity. So, I mean, of course, with more intensity, there's a larger current, but that does not affect the stopping potential. So the energy of the electron. We want the maximum kinetic energy for the electron to make that jump. And what that is the charge of the electron multiplied by the stopping potential. So when we graph this, you have your Kmax against your frequency. This right here is the threshold frequency of the material. So as you can see, there's no energy if the frequency of the light is less than the threshold frequency of that metal. Once we hit that frequency, the maximum kinetic energy goes up linearly. So, since it's a linear function, we can tag an equation to that where your kinetic energy is equal to Planck's constant times the frequency of the light minus the threshold frequency of the metal. And again, the threshold frequency depends on the metal itself. So whether you have copper, it's the same threshold frequency for all copper, but it would be different for a different metal. So multiplying that out, you have your maximum kinetic energy is equal to h, again, Planck's constant time the frequency of light minus another constant right here. So this is how much work is needed to pull the electron out of all the bonds that it's associated with in the metal and jump off. It's what we call the work function. And again, this is associated with a threshold frequency, and that only depends on the metal. It's the energy required for the electron to leave the metal. So we're left with this right here. So this is the energy that has to be carried by the light. This is the only amount of energy an electron can absorb, and again, that only depends on the frequency of the light, not the intensity. The higher intensity, the more electrons, but only if the frequency is large enough to push that electron out. So, in conclusion, just a quick review. The photoelectric effect, what it is when light at a high enough frequency hits a metal surface to knock off the electrons. And this energy is equal to Planck's constant times the frequency of light. So this is the energy of each photon, which suggests that light is acting as a particle. The properties that we have here are, so the current is directly proportional to the light intensity, but keep in mind that it has to be at a high enough frequency. So the larger the intensity, the larger current you get, because the more current, the more electrons are being knocked off. The current appears without delay. So as soon as the light hits the metal is when the electrons start jumping off. This is also suggesting that light is a particle, which we call photons. And so what happens, the light hits the metal, and the electrons, they're only emitted if the frequency exceeds the threshold frequency, and again, that depends on the particular metal that the light is hitting. And this threshold frequency determines the stopping potential. It's the same for both weak and intense light. And the stopping potential is basically the potential that no current is flowing. So what's significant about this photoelectric effect? Well, this is something that we use in solar panels. That gives you an idea of how solar panels work and all those glow-in-the-dark toys that we had as kids. So basically, the photoelectric effect is light acting as a particle and delivers energy and causes the electrons to escape from the surface, creating current. So that is the photoelectric effect.